Hi, today we're going to cover proof by induction. Now, what motivates us to use proof by induction? We don't know what it is yet, but it might help to realize why proof by induction is helpful for us to understand what it really is and what it really does. So let's take a look at a theorem. Now, theorems aren't just theorems immediately. They must be proved, and they can't just be proved in some cases. They must be proved in all cases, at least in all cases that they're purported to apply to. Now, let's take a look at little Gauss's theorem. It says that the sum of integers greater than or equal to 1 up to a number n is equal to n times the quantity of n plus 1, all divided by 2. That is to say, if we are looking for the sum of positive integers up to, let's say, 4, we would get, so let's just denote that like this, 1 plus 2 plus 3 plus 4, and this would equal to 10. And little Gauss's theorem says that it equals to 10 as well. So that's what little Gauss's theorem is. Now, to prove this theorem, you could try every single positive integer. You could try 1, 2, 3, 4, all the way up to infinity. But as you might think already right now, that would be impossible, and it's impossible because that would be an infinite amount of work. Now, here lies the value of proof by induction. Proof by induction does not work by proving every single individual case. Proof by induction works by proving one case, known as the base case. Usually we plug in 1 or 0 into the theorem to see if it works. And then it proves that for any generic number n, of which 1 or 0 is a part of, n plus 1, the next number, will also work. So instead of proving that individual cases work, we prove one individual case, and then we prove that every subsequent number works for the theorem. That is, in essence, what proof by induction does. So, let's review. Proof by induction has 2 steps. 1, the base case step, where you just plug in 1 or 0 into the theorem to see if it actually works. And if it works, you move on to step 2. And in step 2, you prove that for any generic number n plus 1, aka the next number, will also work. And if you prove step 2 and step 1, you prove that any n value greater than or equal to the base case works for the theorem, without having to do an infinite amount of work.